Welcome everybody. This video is on finding roots of complex numbers. Alright, here we go. We're going to start with some examples, check our answers, and then use the checks as sort of a justification for the method that we used. That'll make more sense, I think, after we go through the first example. Here it is. Find all solutions, real and complex, to the equation x cubed minus 1 is equal to 0. Now, just looking at the equation, we know that x equals 1 is a solution. But an important fact is that any polynomial of a certain degree, and this is a third degree polynomial, has that number of real and complex roots. So there are actually 3 solutions to this equation, just one of which is real. Now, to find the other 2 solutions, I'm going to go to the complex plane. Here's our real axis, here's our imaginary axis, and here's the solution that we just found plotted at x equals 1. Now, I'm going to use this axis to find our other 2 solutions, and this is a fact. The other 2 solutions will be equally spaced around the unit circle from this point. So, that means that another solution is up here after a rotation of 2 pi over 3. And the third solution is a rotation of 2 pi over 3 from this point. So down here at 4 pi over 3. Now, all 3 of these vectors have the same modulus, and they're equally spaced around the unit circle. All 3 of these vectors represent points in the complex plane that are solutions to the equation x cubed minus 1. Let's check that and show why. Alright, here's our check. Notice that one of our second solutions, one of the complex ones, is cis 2 pi over 3. If we raise that to the third, we're supposed to get 1 as a result, because 1 minus 1 equals 0. Raising cis 2 pi over 3 to the third is super easy with De Moivre's theorem. We just multiply the power to the angle. So we have cis 3 times 2 pi over 3. The 3's cancel. We have cis 2 pi, and that equals 1. We use a similar process for the third root. Cis of 4 pi over 3, this one down here, to the third power after De Moivre's theorem becomes cis of 4 pi, which is also equal to 1. So, we found 3 solutions to the equation x cubed minus 1 equals 0, 2 of which are complex. Now, before I started the example, I said I'd use the check as a way of justifying what our process was. Here's the idea. When we find one solution, if we pick values kind of around the unit circle that are equally spaced and then apply De Moivre's theorem, those values turn out to be the same value that we started with after De Moivre's theorem is applied. So 2 pi over 3 applying De Moivre's theorem with an exponent of 3 put us back to the real axis at 1, which was the same as our original solution, x equals 1. Same is true of 4 pi over 3. If we apply De Moivre's theorem with an exponent of 3, that puts us at 4 pi, twice around the circle, which is the same as being at 1 on the real axis. So each time we pick values that are equally spaced around the unit circle from our original solution, our first solution, we'll have values that after De Moivre's theorem put us back there. Alright, another example will show us just how easy this is. Example 2, find all roots of z to the 5th minus 1 equals 0. Well, just by looking at the equation, we know that 1 is a root. We also know that because this is a degree 5 polynomial, that we expect there to be 5 roots in total. Remember, these are complex roots, so they can be real numbers or numbers that involve imaginary number I. Well, here are the roots. 1, cis 2 pi over 5, cis 4 pi over 5, cis 6 pi over 5, and cis 8 pi over 5. 5 roots spaced equally around the unit circle. Alright, there's a makeshift illustration of the 5 roots, and I'm trying to make them all equally spaced around the unit circle, and they all have a modulus of 1. Now, a check here would be really easy. All we have to do is think about raising each of these to the 5th power, and notice that we'd end up with cis of 2 pi, cis 4 pi, cis 6 pi, cis 8 pi. All of those rotations put us back at 1. Alright, here we go with example 3. It's a little bit tougher. It's going to involve a little bit of a tweak to our way of thinking. and a little bit trickier algebra, but it's mainly the same. Solve for z when z cubed equals negative 8i. Now, first thing I'm going to do is try to put this into cis form. So, I can rewrite negative 8i as 8 times negative I, and the reason I like to do that is because I like to think of 8 as our modulus, which is always positive. Next, negative I can be rewritten as cis of 3 pi over 2. That's helpful because now I can apply de Moivre's theorem. I have z cubed equals the stuff on this side. I'm going to raise both sides to the 1/3 power. Now I have this. 8 to the 1/3 is just 2. And de Moivre's theorem says to multiply this power to the angle, or the argument, and when I do that, I get pi over 2. So, z is equal to 2 times cis pi over 2. Cis pi over 2, of course, is just I. And z equals 2i. Pause the video for a moment, plug this in for z, and verify that it does equal negative 8i after simplifying. Alright, next thing I'm going to do is plot 2i, and I know that all other solutions are equally spaced around the unit circle. Now, I'm kind of fibbing a little bit with the idea of the unit circle because with the modulus of this complex number being 2, I'm really not on the unit circle anymore. I'm on a circle of radius 2. However, the same exact idea applies. We want to rotate however far we need to so that our solutions are equally spaced, this time around a circle of radius 2. So, we're going to rotate 2 pi over 3 from our initial solution, which was up at 2i. That puts us right here. And rotating again 2 pi over 3, that puts us right here. When we're rotating, we're really just adding 2 pi over 3 to whatever argument we started with, and then doing that again until we have the number of roots that we need. Adding 2 pi over 3 to pi over 2 gets us 7 pi over 6. Adding 2 pi over 3 to 7 pi over 6 gets us 11 pi over 6. Now, pause the video, put these in for z, each individually, cube them, and using de Moivre's theorem, show that we end up getting negative 8i. Alright, here we go with our most challenging example yet. Solve for z with z to the 5th equals negative 4 minus 4i. I'm going to expect 5 solutions because this is a 5th degree polynomial. And I'm again going to try to put this into polar form by finding its modulus and argument. The modulus I find by just doing Pythagorean theorem with these two parts. Negative 4 squared plus negative 4 squared is 32. The square root of that is the square root of 32. And if we picture this on an Argand diagram, or complex plane, we're going left 4 and down 4. That's going to create an isosceles triangle, an isosceles right triangle, in the third quadrant. And so we have an angle of 5 pi over 4. Now, 32 can be rewritten as 2 to the 5th, and if I raise that to the 1/2, that's 2 to the 5/2 times cis 5 pi over 4. That is equal to z to the 5th. Raising both sides to the 1/5 power, I have z equals 2 to the 1/2 times cis pi over 4. Notice that I'm applying de Moivre's theorem there. Now that equals the square root of 2 times cis pi over 4. That is one of our roots, our first one. Now I'm moving to the complex plane, and this first root here in purple is the one that I just found. Now, since these are equally spaced around a circle with radius square root of 2, and that circle all the way through would have angle measurement 2 pi, I'm going to divide 2 pi by 5, and then add that to the argument pi over 4. Pi over 4 plus 2 pi over 5 is 13 pi over 20. Adding 2 pi over 5 again gets me a next root, 21 pi over 20. Again gets me 29 pi over 20. Finally, my last root has argument 37 pi over 20. All of them are equally spaced around the unit circle. The purple one is our first one, and we added 2 pi over 5 to each one, the argument of each one, until we had 5 roots. You can check individually that each of these satisfies the equation up here. Maybe this time try it with a calculator. Alright, that's it for this video.